All right, dear students, dear friends, uh, let's talk about Newton's second law of motion today. Let's have some discussion on Newton's second law of motion. It's a very fundamental law of mechanics. In fact, it's a very basic law of classical physics. The physics that is valid for macroscopic objects like cars, buses, Earth, Sun, Moon, rockets. So what this Newton's second law of motion is? Newton's second law of motion This Newton's second law of motion says that the rate of change of momentum of a body is directly proportional to the net force acting on it. This is one way of defining the statement of Newton's second law of motion. Or I can say the net force acting on a body is directly proportional to rate of change of its linear momentum. So to go with this, if I say that F is the net force acting on a body, of course this F is a vector that should be borne in mind. And dP, the small change in momentum. I'll call it change in momentum. And dt is the change in time. So what does second law of motion say? How does the second law of motion relate these three physical quantities? Momentum is also a vector. That should be borne in mind. So this force must be proportional to rate of change of momentum. This F refers to the net force. This is a key of problem-solving situations. This F is not simply a force. It is the net force. There can be forces acting on a system and their result can be zero. So, taking this force as the net force solves the issues. So, the statement says the net force. It says the net force acting on a body is proportional to rate of change of linear momentum. So if we proceed, we can write F is some K, then d mv by dt. Because momentum is product of mass and velocity. Now, this mass is an absolute physical quantity here. If we choose the situations where mass is absolute physical quantity. And mass is absolute in classical physics, in Newtonian physics. So, if I get this mass out, F will be Km time derivative of velocity with respect to time. Choosing this k equal to 1, I will get F is equal to m. The rate of change of velocity with respect to time is called as acceleration. Or here you can say the time derivative of velocity. The time derivative of velocity is also called as acceleration. So here I'm going to write A. So this is another form of Newton's second law of motion, which says that the net force acting on a body is the product of its mass and acceleration. Now going back to this equation, going back to this, F is equal to dP by dt. You see, if this denominator is small, the force that will be experienced will be large. If this denominator is large, the force experienced will be small. We can take certain examples. Suppose a body, somebody jumps on a very hard floor. He feels a lot of force. He feels a lot of force because the time of interaction between his body and the ground is very small. dt is small there. Now, if dt is small, the force that person will experience will be large. Now, the same person jumping from the same height on sand. Now, in case of sand, what's going to happen? In case of sand, the contact between his body and the sand, that contact will take a lot of time. It's going to take more time. So dt in that case will be large. Now if dt is large, the force that person will experience will be less. So we can say that a person who falls on a hard ground, his chances of getting hurt is large. And if the same person falls from the same height on sand, his chances of getting hurt is less. Because in that case, dt will be large. And the force this man will experience will be less. There are many other examples that can be evaluated on this expression by virtue of physical means. Catching a ball, say for example. Suppose somebody has to catch the ball. And if the catcher moves his hands towards the ball, he is increasing dt. He is increasing this time interval. He is increasing the interval in which his hands are going to interact with the ball. In that case, he will feel a lot of force. Maybe he will lose the ball because he'll be hurt for that moment of time. But if the same person takes away his hands, take away his hands from the ball, when the ball is coming, he'll catch it in a fashion when he's increasing dt. When he is increasing dt, the force he will experience will be less, and he will be in a position to catch the ball. So there are many high school examples that are out there to explain this phenomenon, to explain this relation between the net force and the rate of change of momentum. Now, I think let's try to understand this net force problem. And the best example for this will be the problem of a lift. A person is in a lift, and this lift is going up, this lift is coming down, and at some point, the wire with which this lift is going up, the wire cuts. What will be the weight of that person inside the lift? That weight is an apparent weight. So the problem that we are going to discuss here is the apparent weight of a person in a lift. Apparent weight of a person in a lift. It's not essential that be a person, it may be anything which is on a spring balance, because spring balance will give us the measure of the weight. Suppose there is a spring balance here. I will stand on that balance, okay? The force that I will be exerting on the balance, the same reaction will be from the balance towards me, and that will give the measure of my weight. Now, what this problem is all about. So we would like to see first, there is a lift, and in this lift, there is a person in it. And his apparent weight is, say W. And this lift is fixed with something. It has a rope. And this lift is going up. This lift is moving up with respect to the ground. Now, what are the various forces that will act on the person standing in this lift? So the very first situation that we are trying to learn is when the lift goes up. What's going to happen in that case? When the lift will go up, its direction of acceleration will be this. The rope will have a tension in the upward direction, and the gravity of Earth is always attracting it. So that gravity will be mg. And this tension in the rope will give us the measure of the reaction of the lift to the person standing in it. So this P will give us the apparent weight of the person inside the lift. Now, what Newton's second law of motion tells us? It tells us the net force acting on a body. So I have to calculate that net force. What is that net force? Okay, the lift is going up, so T must be more. Minus gravity is opposing this T, but the lift is going up. It must be equal to ma. So this T is the measure of apparent weight of the body inside the lift. So instead of this T, I should write W minus mg is equal to ma. So W is m times a plus g. This will be the apparent weight of this person inside the lift. Now suppose, for the sake of argument, if I say that there is a person inside the lift and his mass is 30 kilograms. What will be his apparent weight if the lift is going up with an acceleration 2 meters per second square? And let me choose g is equal to 10 meters per second square. So what's going to happen here? Okay, so what's my equation of apparent weight in this problem? That is W is equal to m, that's 30, times A is 2 plus 10. So W is 30 into 12. So if we calculate his original weight will be, suppose that is W1, that will be 30 into 10, that is 300 Newton. Obviously this product will give us the weight more than that of 300 Newton. If we write down this is 12, this is 0, this is 36. 360 newtons. So you see, this is the original weight of the person on the ground, and this is the weight, the apparent weight that he has when the lift is going up with an acceleration 2 meters per second square. So this value is signifying that the apparent weight of this person increases when the lift goes up with an acceleration 2 meters per second square. Now let us discuss another case. Now another case is what? Another case is the lift is coming down. So the lift is coming down. Now if the lift is coming down, what will happen to the acceleration? The acceleration in this case will be downwards. Obviously, I have to write down the net force acting on this lift. What will be that? So which one is greater? It is mg minus t. This is equal to ma. So this is mg minus, what is this t? This is the apparent weight of the person, is ma. So this w will be mg minus ma. So this will be m times g minus a. The equation is simply telling us that the weight of this person is going to, apparent weight of this person is going to decrease when the lift is moving in the downward direction. We can choose the same problem that we chose for the lift when it was moving in the upward direction. Now, what was that problem? What was the apparent weight of this person on the ground? That was W1. That was 300 Newton. And what was his mass? It was chosen 30 kilograms. Now, if I use the same thing here, what will be W apparent for him? That will be M. M is 30 times G is 10 minus 2 is acceleration with which this lift is going down. So what will I get here? I will get WA is 30 times 8. 240 Newton. What has happened to the apparent weight of this person? The apparent weight of this person has decreased when the lift goes down with some acceleration. Now, the last case, a very important case, is the free fall. Free fall. This lift is coming down, and at some instant of time, its rope is cut. When the rope is cut, the lift falls freely in air. That means the acceleration with which the lift is falling and the person in the lift is falling, these two accelerations must be same as that of acceleration due to gravity. So what was the apparent weight for a falling lift? It was m times g minus a. But when you have a free fall, this a must be equal to g. So w in this case is m times g minus g, that is equal to 0. So what is the result here suggesting? The result here is suggesting that the apparent weight of a free falling body is always 0. That means if somebody is on a window and he's jumping onto the ground, during his fall, his apparent weight is 0. Cannot measure his weight. His apparent weight is 0. This is what is called as free fall. So during a free fall, the apparent weight of a body is 0. I hope you get some of the idea as I have discussed. Maybe it will be helpful to you, to anybody out there who can have even a fraction of benefit will certainly give pleasure to me. I'll feel very great about that.